Good morning, everyone. Before we start, this is a reminder that as registrants through your attendance at or participation in AAAS annual meeting sessions, you've agreed to permit AAAS to use and distribute, both now and in the future, your image or voice in photographs, video, audio, and electronic reproductions of such events and activities. So please be mindful of this as you participate. Welcome, everyone, and thank you for joining our scientific session on building a resilient energy grid to respond to escalating hazards. My name is June Bondo, and I'm the Senior Advisor to the California Council on Science and Technology, or CCST. I'm speaking to you today from Sacramento, California, the tribal lands of the Nisenan people. Sacramento was a gathering place for many local tribes, and so we also acknowledge the Southern Maidu people to the north, the Valley and Plains Miwok peoples to the south of the American River, and the Patwin-Wintun peoples to the west of the Sacramento River. I'll begin by introducing CCST's Disaster Resilience Initiative and the topic of our session. CCST is a nonpartisan, nonprofit organization that connects science and technology experts with policymakers to enable evidence-based decision-making. We do this through a number of mechanisms, including briefings, workshops, reports, and the CCST Science Fellows Program, which places PhD-level science, technology, engineering, and medicine professionals in state government offices for a year of public service and training. We've sponsored this session as part of our Disaster Resilience Initiative, which focuses on strengthening preparation and response to complex and intersecting disasters that affect public health, our economy, and the environment. I'm honored to be moderating this session with our three distinguished panelists, Dr. Varun Rai from the University of Texas at Austin, Alona Tiber from the SLAC National Accelerator Laboratory, and Dr. John Paul Watson from Lawrence Livermore National Laboratory. I'd also like to thank my colleague, Dr. John Thompson, for organizing this session. Our conversation today will explore hazards threatening the energy grid and mechanisms for improving resilience to extreme events. Today, large-scale threats to the electrical grid from extreme events are becoming increasingly common. Grid disruptions from man-made threats or natural disasters can cause catastrophic consequences, such as loss of life, economic losses, or national security breaches. We can increase grid resilience to these kinds of events through a variety of pathways, including by predicting extreme events, adapting operational policies, deploying new technologies, and hardening critical infrastructure. We face a number of opportunities and challenges in applying technological solutions and operations practices to better predict, mitigate, and recover from the consequences of large-scale disruptions. Today, we'll be hearing from our three expert panelists on these issues. Each panelist will introduce themselves and then briefly share highlights of their background and research. After that, we'll transition to Q&A. For the audience, please use the Q&A feature to submit your questions to our panel. And we also ask that you include your name and affiliation. And now I'll turn to our panelists for their opening comments, beginning with Dr. Varun Rai. Over to you, Varun.
Great. Thank you so much, June, for that introduction. And I'm very delighted to be joining you all. I'll keep my comments brief and at a high level, and we can get into more details during Q&A. As you mentioned, June, let's start with the notion of resilience, but to what? And you mentioned many different factors which are impinging upon operation of the grid, and the interplay of those and the evolution of all of that is going to be very, very important, because there are many different factors, including obviously climate, but then also what's happening in terms of cyber. We have learned a lot about supply chain disruptions, and the grid is not immune to that either. All of that can also scale up to human level and societal level disruptions and migrations, right? When you bring in climate change and what could happen in some of the worst case scenarios. So one question to keep in mind is resilience to what, and all these factors at some level are actually quite intertwined, and that plays a huge role. So, and I would like to put forth 5 basic ideas of what I believe are very important as we think about resilience of grid moving forward. One is to plan for the future and not the past. Rapid electrification is expected and needed largely because of greenhouse gas emissions and our ability to control those and mitigate those. But how exactly we get there is still up in the air. There are many different routes, and no one is singularly better than the other. There is tremendous heterogeneity in conditions, resources, needs, and capabilities across the world, and even within one country, for example, the US. So it's very important to keep that in mind. And every technological trajectory will come with its own set of challenges. Nothing is foolproof, nothing is singularly superior. So building redundancy into the system, being ready with contingency when things go wrong, and actually expecting that things will go wrong. I think these are some very basic design features, but are centrally important. The second thing I'll mention is making electricity systems more efficient, not just the technology. So often we focus on efficiency of technologies and buildings and cars, and that's really good, but that's only part of the solution. We have to keep in mind that these technologies operate within a larger socio-political institutional complex. If those are inefficient and ineffective, and they often are, then just efficient technologies would not help us much. A very good example was what happened last year, exactly around this time in Texas, in the wake of Winter Storm Uri, which led to widespread blackouts, tens of billions, if not hundreds of billions in losses, hundreds of deaths, and all of this because deep and long blackouts that happened here. One of the key lessons that emerged in the aftermath is how poorly integrated and coordinated the whole system is. Not the technologies, not the power plants, not the transmission system, but also the institutional systems coordinating, integrating all of this, leading to many defects in the overall system design, which crippled system response during shocks, thus failing to contain damages and impacts. And that's what resilience is actually really about. It's not about performance of the system under certain known operational range of operational conditions. Rather, it's the response of the system when you're out of equilibrium, when there's a shock in the system. And so it becomes very important to keep an eye on the system and keeping the system sufficient and effective. Third point, very quickly, is we should build systems that not only solve current problems, but also are less likely to create new major problems. So, for example, we think about greenhouse gas emissions. What happened 3, 4, 5 decades ago, and maybe a century ago, those were great, and we kept investing and building, but they led to something that we are now faced with, which is really massive. And there are many solutions on the table. We should be humble to recognize that even many of those could lead to other types of issues. And we know about several of those. For example, in terms of supply chains, in terms of rare earth minerals and what that does, both in terms of the materials themselves and the nature of the materials, but then also how it interacts with where it is being produced and the people and the communities there. So we always need to keep the aspects of redundancy in mind, alternative solutions, R&D. We cannot close off pathways to new possibilities, assuming that the paths we are on and the current solutions are going to be great. And two final points quickly. It all has to be for people and by the people. Engaging communities is very important. Justice and equity are going to be critical, because some of these changes that we are seeing and that need to be sustained for the next 3 to 5 decades, leading to a very, very different system compared to what we have, that needs long-term social support to really enable that type of transition. And being inclusive creates more benign underlying conditions for such long-term systemic change. If not, then the resulting social unrest and upheaval could undo, reverse, the more simplistic and unidimensional progress based on the logic of just economic efficiency. And we have seen that play out actually in the last few decades. And my final point, which I think is actually perhaps the most important point, which is this is a complex system. Grid is perhaps the most complex, socio-technical system humans have created. And with more electrification, including in transportation and the industrial sector, it's set to become even more complex. So we should be very humble about our understanding of such systems, and always try to learn more about its nature. And the only way you do that is through experimentation and learning through that experimentation, changing a little bit and seeing how the system responds and learning about part of the system's nature. But this part is very, very poorly understood by policymakers, by stakeholders in the industry, by utilities, and it makes very difficult to form really productive long-term conversations and partnerships to move this frontier along. But more than ever today is it's even more important to keep experimenting and learning with the system. So I'll leave my opening remarks there and then look forward to the discussion.
Thanks so much for those very insightful opening remarks, Varun. And over to you, Alona.
Yeah, thank you. Thank you for having me on the panel, and thank you, Varun, for kind of setting the problem up for us. I think that was a really great introduction. Yeah, I just really want to echo on the points that are already being made and bring up the next one in terms of resilience being so highly dependent on the timescale that we're talking about. So some of the things that we've found within our group at Slack while talking with utilities and stakeholders of the issue is that anytime you talk to somebody about resilience, they have a very different definition of what it is. And a lot of it is so highly dependent on the time scale that we're talking about. So are we talking about the long-term climate adaptation side of resilience, or are we talking about what is happening in the next 2 weeks with the wildfires and the winds coming through, or are we talking about when are we replacing the poles in the system? Are we going to be replacing them next year, the year after? Is this one good enough for to kind of make it through this next windstorm, or do we need to replace the whole system? And then who is paying for these replacements, and how do we optimize them correctly in order for this idea of safety and equity to be maintained while we're also powered up and ready to go? And one of the most kind of interesting points about resilience is that it really just touches on every different facet of the technologies, whether it's electrification, whether it is integration of DERs, whether it's supply chain, whether it's just safety and just kind of at its core. So our group at Slack is focusing mostly on the distribution system side of things. So we've seen or we've heard about the public safety power shutdowns that are being executed, especially in California, due to big windstorms to prevent wildfires. So one of the things that we've learned is that these mitigations are not necessarily being considered through the distribution system aspect. And so we're not taking into account what are the behind the meter resources that are available to the communities, what is the rate of electrification in the community. And this all plays back into this equity component and metric, you would say. So a lot of the approaches take kind of the techno-economic objective and the constraints. However, more and more in day-to-day, we're realizing that technology or the economics don't necessarily work out for the best for the community itself. So I don't want to rant on for too long and kind of just want to make sure that I echo Varun's points on electrification, distributed energy resources, and climate adaptation in the long term, but also maintaining that resilience on the short term. And those could be these competing objectives that we're not quite thinking about when we're thinking about the primary impacts and taking care of the secondary and the tertiary impacts, as well as kind of seeing the picture in kind of a large scale and kind of taking a step back. And I find that that's really an important point of resilience, as well as a number of other aspects that come together in play. Thank you.
Thanks so much, Alona. And JP, over to you.
All right, a lot of good points discussed already, so I'll highlight a couple of ones that I didn't exactly hear. The first one is modeling threats. You can't be resilient to everything, so the stakeholders need to get together and understand and characterize what specific events and classes of events they want to look at. I think that's a critical aspect. So in California, we care about wildfires, droughts, things like that. Polar vortices, not so much. So, hurricanes hit certain regions of the U.S. Those stakeholders should care about and model the impacts from potential future hurricanes there. So modeling threats is a major issue. This pops up a lot when we're trying to, as DOE has a lot of modeling and simulation efforts. What you want to do, we have multi-infrastructure models that look at gas, communications, electricity coupled, but the input to all of that are a set of contingencies that are associated with a particular event you want to analyze. So it could have been the February 2021 event in ERCOT, but you would like to project which components will go out, do the simulation, understand what the cascades are, and then quantify resilience and impacts based on that simulation. But it all comes down to modeling that threat up front. If you get that model wrong, all your results downstream will be wrong. So garbage in, garbage out. So that's one thing I wanted to say. Second one is resilience metrics and quantification. This is a hot topic, has been for a long time. Unfortunately, there aren't really well-established resilience metrics. Like, not everybody agrees on this is the metric, here are the inputs. A lot of when you talk about resilience, it's not so much megawatt hours lost, but it's actually who it's lost to, what the economic impacts are, what the social impacts are. That kind of data is not readily available. It usually takes a lot of effort to get that data and integrate it into our models. So I just want to reinforce the fact that resilience metrics are important, but they require a lot of soft and kind of data that power systems type people usually don't have access to. And that makes it very hard to actually roll those up and compute those. And the third point I'll make is, Rune talked about this, all of this is centered around, in order to be resilient, you need to be kind of hedge yourself against all these possible outcomes of what might happen in the future. So my research expertise is in decision making under uncertainty. So the goal there is to get projections of what might happen. For example, maybe climate model A is better than climate model B. Maybe there's a model C that actually is the real one that's going to be the most accurate. You need to understand and project future possibilities, but you need to react now. So we have to build things right now. We have to try to get to 100% decarbonization goals in the next 10, 20 years, but we have to make decisions right now, but we don't really know where the climate's going to go. We don't know which model is best. We don't know how consumers are going to react to price changes in solar and EV and market policies, things like that. So it's all about trying to understand projections of where the future is going to look like, and many of those, but also you have to take that set of projections and actually do something right now, and that is decision making under uncertainty, and that's, I think, the hardest part about this entire effort. That's all. June, you're on mute.
Thank you, JP. And thank you all for those really insightful opening comments. One of the issues that you've all highlighted is the difference in preparing for different types of threats. And so I'd like to ask you to talk a little bit about how preparing for natural threats, such as storms or wildfires, differs from preparing for intentional threats, such as those posed by malicious cyber attacks. And more importantly, what are some of the trade-offs as we think about designing resilient systems for these different scenarios? We all recognize that we're talking about very complex systems and a lot of uncertainty surrounding future scenarios.
I can start with a general comment. So both natural and intentional threats are highly correlated. You generally get a lot of failures. You don't just get one or two. It's not N-1 and N-2. It's N-K, where K is big. It's the nature of that correlation that really differs. So, natural events like wildfires and hurricanes, they're going to take out components in a particular geographic region. You can kind of get a characterization of where that is. So the correlation there comes from geospatial sources. For adversaries, they can model the grid. They know where they can compute where weak points are. So the correlation there is the fact that they have the same models that you do, or some representation. They can do some analytics, and they can understand here are the choke points that you care about. So a cyber attack might actually take out components in Montana, New Mexico, and California concurrently, whereas a natural event would never do that. They're still correlated in the sense that the threat is being computed over a big model, but the correlation is just very different structured. And I should also say that the adversaries, assuming they're smart and capable, they can actually induce much, much higher impacts than a natural event will. If you look at distributions of, if you pick random K components or even like a cold wave, things like that, even though it looks bad, if you give an adversary that's intentional the same budget for taking out that number of components, they're going to do way worse. You're going to be far deeper in the tail.
And I'd just like to add that generally with kind of taking approach to resilience and the modeling is broken down into three main components. So the anticipation, absorption, is recovery is something that you hear a lot in the literature. And the good thing about the absorption and the recovery part of things is that the system doesn't necessarily care what the threat is. It just addresses it, and there's algorithms that mitigate for these events. But the challenge is really with the anticipation side, where this is something that we run into a lot, is the data component, or a better way to describe it is the lack thereof the data component, because these events are so sparse. It's hard to have a large data set that can really characterize how these events will happen. And that's really where the main differences are. So the anticipation part is really just where the challenge lies with differentiating between a cybersecurity event or a weather event. And the weather event has a bit of an advantage in the anticipation stage, because we've had weather events before. We can characterize them. However, their magnitudes are increasing, their frequency are increasing, especially with areas that don't normally see these events. So we're seeing wildfires in California. However, they're starting to spread all over the nation and starting to have impacts all over the nation in areas that they have not seen them before. So how do you prepare for something that you've never even seen before is something that the grid is also facing, and not just the society themselves.
June, only thing I'll add to that is also how you prepare for these two different things has a little bit of a different aspect. And there are many common things, as JP pointed out, but if, or more on the natural hazard type of things, those could be, local or regional, as JP pointed out. And so those might involve certain type of, physical or hard infrastructure reinforcements, or, even reactions and response, and might be limited within the space of a utility or a state or so on. As JP pointed out, once you go to more of the cyber physical aspects, then the way you try to address that may not necessarily always have a physical basis to the solution. So that's obvious. But the second piece is who is on the table to even decide on those solutions and collaborate. It just working within a utility or even within a state will not get you much farther. Right, so that's important. I want to kind of pick up two other points. One that Eleanor mentioned, and the second that JP mentioned. On demand side and behind the meter aspects, and to JP's point on quantification and metrics for regarding resilience. So on the demand side, so this is, if you ask what has the biggest change, that has changed in the grid and in the electrical system in the last decade, 2, 3. Is actually the nature of the demand itself. Historically, demand always has been taken as a given, right? Here is what we expect from the demand. Here is what the curve will be, and let's just try to supply it. And yeah, there are going to be. Let's manage the supply side uncertainties and risks. That's been the nature. What has happened because of technology, demand really has changed, and it's not just your solars and EVs, but also your smart thermostats and all types of other gadgets, and also means of aggregating some of that. And that has made demand very, very dynamic. It shows up in two ways. One is it can surprise you, as we learned in Texas. Even the most aggressive projections of what demand could be were actually blown away, and demand was actually higher. That was last year. This year, the projected we had much lower temperatures for a couple of days, below freezing. And demand was projected to be very high, and actually the actual demand undershot that by like 10, 15 gigawatts, right? So, that continues to be very, very dynamic, but it's also a great resource, right? In the very short run, there's very little that can be done with supply. There's very little, right? You only have that much gas in storage. If your pipelines are frozen, sorry, you can't move any more gas, right? If you don't have sun or the wind is not blowing, you can't generate more. But you do have the demand that is, trying to consume based on what's needed. That needs to be pulled in a lot more proactive way, and that has been happening. But I really think that that's a huge lever that has not been really put to good use. But it's also important, given something I said earlier, which is given the types of changes we need and expect in terms of electrification and decarbonization of that supply over the next several decades globally, all of those trajectories face major challenges. Be it renewables integration, storage aspects, and long-term seasonal, and weather management, but then also aspects of siting and transmission and whatnot, right? There's nothing that is very obvious, because if it were, we'd be sailing. And if that is the case, if the supply side, no matter which, is bottlenecked, we have to really push very hard in managing demand and being very efficient there. So I just wanted to raise that. And then very quickly on JP's point on the impacts and damages really being the core of what we try to deal with in terms of resilience. There was a study last year by some colleagues at Lawrence Berkeley Lab and a colleague at UT Austin, Ben Leibowitz, that looked at these types of metrics. And one of the things that they found is the metrics and quantification of outside of the system impacts, right? So for example, loss of productivity, loss of life, other types of damages and so on. There is very little data on that. And part of that is intentional, part of it is because it is too complex. But unless you have that data, your question, June, on trade-offs, it's really a very hard to answer. And in that is, I've spoken many times over the last year that we need to bring that part of the equation, really do a much better job of quantifying that, understanding those damages and impacts, and then talk about here are the investments and so on as a trade-off. Otherwise, we are just shooting in the dark saying this is more or less expensive, but in the context of what? If you're not doing this, okay, are you ready to put $100 billion bill every 10 years? So that really is a big missing part of the equation.
Thanks very much for that, Varun, and thanks also Alona and JP for your insights. We have a question from the audience from Aaron Reagan at the University of Pennsylvania, who says, I'm very interested in the economic and financial component of this larger discussion mentioned several times already. Could you further discuss the competing forces and stakeholders involved, as well as any insights and best practices that should be considered and implemented?
I'll say something on the financial trade-offs that I think is important. There's obviously a lot of stakeholders. There's DOE, there's DHS, there's utilities, there's investors, there's consumers, there's all of that. But I think the hardest part about resilience is actually getting those projects funded and making the rate case for it. So, when you look at things to invest in, you could say this is going to maximize your resilience, but if it doesn't have impacts on reliability and kind of normal blue sky events as well, then it will probably never get built unless the federal or state governments step in and do that. So I think the things I would want to build are the ones that I do resilience analysis, and I get maybe a suite of 5 or 6 things I could do. I want to immediately then look and see how does that impact kind of nominal economics, but also reliability, because I think the things that are highly correlated are things that are most likely to get funded, and that's probably where we want to start.
Thanks for that, JP. Varun, I wanted to ask you if you had anything to add to that, acknowledging that you have a really interesting background and you've looked at this perspective, from a public policy perspective, as well as an engineering perspective, and you've also served as a regulator in the space.
No, totally. I think JP's comments are extremely well placed here. I'll just add that what the community wants and communities want and how that flows into actual decisions and investments, it's a very complex and tricky process. And I was a regulator for Austin Energy, which is Muni here in Austin that supplies. And one of the biggest learnings for me during my time was how engaged the community itself was, and communities' preferences were much more closely discovered and reflected, and because of that brought into decision making. Not perfectly, but reasonably well. Now, the stakeholders on the table, they all have different time horizons and they all have different interests, and that matters a lot. Folks who are driving some of these decisions and bringing different folks on the table. So, for example, some utilities, they have a very different time horizon. They have a different holding power. They have different incentives. And just by steering the conversation in certain ways, or structuring certain types of reports and reviews certain ways, or extending things beyond a certain time horizon, continues to give them a lot of leverage and say in a way that can diverge, or at least not in short time frames may not really be very well aligned. So, and I think that becomes very important to keep in mind as well. One final thing I'll say in terms of finances is a lot of something I already touched upon in my initial remarks is there has been a lot of focus on economic efficiency, and that is very important because resources are limited. We're talking about big changes, and it's not going to be easy and simple. And yet, that should be only one part of what we should really be focusing upon. It cannot drive all our decisions. And so I'm part of an ad hoc committee of the National Academies that looks at deep decarbonization in the US. And it has 4 pillars of what are important, and economic efficiency and cost effectiveness is actually just one of those. And the others really focus mostly and largely actually on the social and human dimensions and justice and fairness. And as I said, not bringing those into the equation of decision making really exacerbates the situation. It robs us of the opportunity to really align things better and do good on the wrongs that have been done historically, but then also doesn't create really the right long-term conditions for deep, continued social support for this type of systemic change.
I just have one more quick point to add on this as well, and really just kind of bringing it back into the equity component of the discussion. The idea that the incentive, I think that a lot of the resilience incentives are quite similar to what we've thought about for climate change as well. And so to bring these incentives to underprivileged communities is a big challenge. So for example, if you're promoting solar in an area or batteries, how does the renter community benefit from that? And that is something that they could use for their own resilience ideas. And to give another example is kind of back in the electrification space. If you could use your EV to support your house, then great, you have your power while there's a resilience event and the power is shut off. However, how does the underprivileged community who can't afford an EV, since they're so brand new and the adoption rates are generally from the middle to upper class, how do they also benefit from that? So these are some of the things. And for example, another example is in the microgrid space. So of course we can build a microgrid for a renter or a small community. However, they don't have control over that, right? And so if they don't have that access, then how do we make sure that not just the upper class is doing just fine like they have been, and how is it that the folk that is really just the mass is also taken care of? And so that's one of the big trade-offs that I think is so important to think about as we talk about not only climate change, but resilience as well.
And I'll go on to say that what Elena just described is actually going to get much worse. We should expect more of these disruptions, more on the physical side as well as the cyber side. Humans are not perfect learners, but we do learn from experience. And the capability to react to those experiences, especially when it comes to investments, is very, very unequally distributed, right? So, the folks who are well-to-do will have their EVs and batteries and storage solutions and more efficient homes. And what that would mean, and utilities and regulators will anticipate that. And so there is a possibility, again, I'm not saying this is a given, but there is a possibility where you see the infrastructure actually evolve, or at least in certain parts where there's a decoupling between what really a systemic response to resilience is from an infrastructure perspective versus what individuals start doing en masse. And then things would get actually much worse for folks, for the lower income folks. And there is no, already it has been a pretty bad situation in terms of how these issues are addressed. But in that scenario, it's going to be much harder on certain sections of the society, and that's the type of thing we should anticipate and really try to have a systemic response. Because if we leave the pieces to just fall and reassemble and take care of themselves, there is a pathway that makes the situation much worse.
I think a lot of local, in the slight defense of local planning entities, like I was in conversations recently with the city of Livermore, and their focus, they want to use the electric buses that we have here to basically react in the case of wildfires and when there's public safety shutoffs. And they're worried about getting those to cooling centers, to drive the cooling centers to maximize benefit to those class of people. So I think that's I think at least is interesting discussions that they're starting to have to figure out how they can use microgrids and kind of city resources to actually achieve equity in that context.
That's absolutely right on, JP. And that's exactly the type of proactive thinking that we are starting to see in some places and needs to happen a lot more. That can still get us in a good state that we all can live with and be happy about and not get into the dark scenario that I described.
So thanks to all of you for highlighting some really important aspects of this discussion. Alona, you brought up the equity piece, and Varun, thank you also for diving into that. And I think a recurring theme throughout this conversation has been the need for a systems perspective to addressing grid resilience. As we think about opportunities and challenges to that kind of systems level approach, I'd like to ask all of you for your thoughts on what are some of our most pressing gaps in knowledge. I know that's a difficult question. We've touched on some aspects of this already. What are the biggest barriers to building a resilient grid that remain to be addressed?
Figuring out how to pay for it. I mean, being partially serious, but I think it's when they see the numbers, it's just stunningly large. If you actually want, and I think a lot of it has to do with people don't understand the resilience cost trade-off. So there are going to be situations where we're going to lose power. There's going to be the ERCOT events. It doesn't matter how much we invest in the grid, that's still going to happen. The question is how often we want it to happen and how big the impacts are. So I think educating stakeholders and actually being able to compute the risk-reward trade-off is critical, because maybe the reward, maybe there's a drop-off at some point where there's diminishing returns once you spend $10 billion to underground lines, let's say. Being able to communicate that is really important. Bad things are always going to happen. It's just how often we want them to happen and where we're trying to mitigate. I think just trying to figure out how to communicate that and compute those metrics or those trade-off curves is critical when you're trying to talk investments.
I'd also like to add, as one of the gaps, is really the data. And I think I've mentioned that earlier in this discussion. And I think the data is out there for a large part of it, but does it integrate together? And it has no value unless it comes together into an insight that is actionable by the utilities or the stakeholders or regulators. And so it's hard to, it's kind of one of those like chicken or the egg problems. Like, do we need to figure out what data that we need, or do we need to figure out what data that we have and how to integrate it correctly? And so talking with different utilities have different data sets that they collect. And it also matters about the scale of the utility. So maybe the IOU will have vast amount of data that they use. However, smaller co-op may have a much smaller accessible data set that they're collecting, because their issues are not quite at the resilience level yet, that they maybe not be able to mitigate. And eventually, I hope not, but eventually they might be facing the same problems that the IOUs are having. And so, yeah, data.
Yeah, I'll reinforce that data, like I mentioned before, but like, power systems are run on models, mathematical models. They're used to operate the grid. And, when you worry about like these extreme events, people again talk about, megawatt hours lost, and they just talk about the total number. And, until utilities are coupling kind of impacts like, equity measures and things like that, those data layers into and overlay them on the models that are used to run the grid, it's hard to see any decision being different because they're not exposed to those metrics. So I think, if you actually said, yeah, it's 10 megawatts lost, but it's like, at this hospital or this senior center, that's going to cause differences in thinking. Whereas if it's at a suburb where everyone's, well, I guess pre-pandemic was, commuting into work somewhere and they're not there, it's not going to impact too much. So to me, getting that coupling of the data, once people start seeing the layers on top of their infrastructure models, then you can start making decisions. But until that happens, it's not going to.
And I will add one other thing, which is an integrated thinking and openness. This is not just about one part. This is not just about electricity. It's connected to gas. It's connected to supply chains. And so having that, really holistic view, and JP alluded to these types of interdependencies and contingencies earlier. And there's a tendency to be short-sighted, to be siloed, and some of that tendency actually is reinforced through politics. It's not always, a permanent choice, but it gets reinforced through this, social political interaction. And there's no easy fix to that. It's something that will evolve, and there are great lessons and experiences and experiments that are happening on the ground that will shift the understanding, but wherever you're seeing real progress towards this, it has a central component that is this integrated understanding of all the components together, and being open towards them, and not going back to that siloed thinking, be it institutionally or be it from design perspective.
Thank
I think
you.
the openness. Oh, sorry.
Go ahead, JP.
A real quick comment. I like the openness angle that was Rune just brought up, because to me, it's like when people are doing analyses and making decisions. I was talking about threat models earlier. So California is going to plan under certain assumptions about where wildfires are going to be and how prevalent they are. But unless those assumptions and models are exposed to everybody involved in the stakeholder process, it's hard to get everybody on the same page and make the same common understanding about why things are being made. So in my mind, transparency is critical, both on the which operations models you're using, but also what threats are you considering, and the whole spectrum. So if you're not able to be transparent, it's hard to justify and explain what you're doing.
Thank you. Well, our time here is quickly drawing to a close. And before I wrap up, I just, first of all, want to thank all of you, but also want to pause here and ask if anyone has any really quick final thoughts that you want to share, particularly, if you've got any thoughts about what you're most hopeful or excited about in this conversation.
I think I'd like to say that it's really exciting that we're having these conversations to begin with. And I think bringing awareness to not just everybody that's in the scientific community, but also in the public is so important. And I really hope that we continue to have these conversations.
Thanks, Alona.
I'm most excited right now about work we've started as a national lab system, and also industry does this too, but we're starting to couple climate models with infrastructure models and trying to understand what those impacts are. To me, that's the most exciting thing out there. And I know a lot of national labs have started doing research efforts in this area, including ours. But to me, that's, if we're going to impact the world in 50 years, that's the kind of work that needs to be, done and extended.
That's great,
Thank
JP. You and I need to connect offline. I have a great team of colleagues here at UT who are doing some really interesting work on very similar lines. My final thought would be, this is actually a very exciting time. For a long time, electricity sector was actually known to be very boring and perhaps the least innovative. That is anything but true right now. It is perhaps the most dynamic sector as we speak. Something that has changed dramatically is how capital has really flowed in because of all sorts of expectations, because of climate change and so on, but then also what's happening with hazards and impacts. And there now, what I'm seeing is the forces that are really fundamental to generating long-term deep innovation have actually aligned. So I'm actually very, very excited to see, and I'm very hopeful that those will really help us address these things and move in and land in a situation and scenario that is socially puts us in a better place.
Great. Well, thanks so much, Varun, Alona, and JP for your time and your insights today. I'd like to thank everyone who joined us in the audience, and also thank AAAS for organizing the conference. If you'd like to learn more about this topic, and this is for our audience, be sure to check out our panelist spotlight videos. If you'd like to learn more about CCST, we invite you to visit our website at ccst.us. We also welcome you to visit the CCST booth in the virtual expo hall to learn more about our Science Policy Fellowship program. Thanks, everyone.
Thanks, everyone. Thanks, June.
Thank you all.